Enthalpy, Part 1, Thermochemical Equations. We're used to writing chemical reactions this way. We have reactants always going to products. And we've never talked about heat, but so many reactions are heat dependent. Either these reactions are going to give off heat or they're going to absorb heat in order to move forward. So what do you do with this heat? Well, we're going to treat heat as a reactant or a product. So to make a reaction a thermochemical equation, all we do is add a delta H, an enthalpy of the reaction. So if we have a chemical equation and a delta, along with a delta H listed, it all of a sudden becomes a thermochemical equation. So I know it's odd to consider heat as a reactant or a product because we can't see it, but we can definitely see its effects. Knowing how to use thermochemical equations is going to allow us to make really good predictions on just how much a chemical reaction is going to heat up, how much heat it's going to produce, or how much heat it requires in order to react. Let's start our discussion by calculating the kinetic energy of one single molecule. So the kinetic energy of anything is this equation: 1/2 the mass of the object times the object's speed, and the speed has to be squared. Now, if you want the units to work out, the metric unit for energy is joules, capital J. Mass needs to be in kilograms if you want joules, and speed needs to be in meters per second. So if you want to calculate the kinetic energy of a molecule, it'd be 1/2 its mass of the molecule times its speed squared. Why mess with kinetic energy of molecules? Well, heat is temperature, and the higher the temperature, the faster things move, so the more kinetic energy they have. One last little idea here is the mass of a molecule is going to be the molecular weight all over Avogadro's number. And the reason why this works is because molecular weight is the mass of Avogadro's number of them. So if you divide the molecular weight by Avogadro, you get the mass of one molecule. So let's watch this movie to get initiated into the terminology that's involved with reactions involving heat.
Let's analyze the changes that occur in energy and atomic arrangements as the reaction between nitric oxide and ozone occurs. Initially, the nitric oxide and ozone molecules are separated and are not reacting. The forward reaction proceeding from reactants to products is exothermic by 199.8 kilojoules per mole. Let's see how the energy changes and the molecular changes correspond. As the reactants approach, their energy increases. When the molecules are in a transition state or activated complex, their potential energy is at a maximum. As the transition state is passed and the molecules become more like products, the potential energy decreases. Finally, the molecules reach the energy state characteristic of the products.
So here's the beginning of the reaction. And here's the end of the reaction. Beginning, end. The difference in energy between the beginning, the reactants, and the products is delta H, the enthalpy of the reaction. That's the energy difference between these two reactants and products. So these are the reactants, and these are the products. The energy difference between the reactants and the products is delta H, the enthalpy of the reaction. That's the energy difference between reactants and products. In order for all reactants to produce products, they need to go through a transition state. And all that is a special geometry of the molecules, and they're just in the act of combining and doing the reaction. And it takes energy to do that. That's why you can see they kind of came up in a little energy hump there. So let's see if we can answer these questions. In the plots to the right, which describes an endothermic reaction and which describes an exothermic reaction? So let's call the blue one reaction 1 and the green one reaction 2. Endothermic. Remember what that meant? That meant that the enthalpy was greater than 0. It was positive. So the reactants had to absorb energy to become products. The products are at a higher energy. That would be reaction 2. If the reactants are low, products that are at a higher energy, that'd be reaction 2. Exothermic, remember that's where the enthalpy of the reaction was less than 0. In exothermic reactions, heat is given off. You start at a high energy, you end up at a low energy. You get a negative delta H. So that would be reaction 1. Are most reactions in nature endo or exothermic? Later, we'll talk about entropy. And entropy is the reason why most reactions in nature that are spontaneous are exothermic. And we'll talk about that later. What is EA on each of these plots? EA is the energy of activation. And if you remember that movie, the reactants, in order to get to products, they had to overcome an energy hump. Here it is. Well, just how much energy did those reactants have to overcome? That's what EA is. On the endothermic reaction, EA is a lot higher because your reactants are way down here. The energy hump it has to overcome to become products is this huge amount of energy. The energy of activation is very large for endothermic reactions. What is the reaction coordinate? Again, if you remember the movie, it's just where are you at in the reaction? Are you at the beginning or are you at the end? That's what reaction coordinate describes. Why is the enthalpy of reaction the same on both plots? I think it's important to sketch in this enthalpy of reaction. If we look at reaction 1, there's our enthalpy of reaction. It's the energy difference between the reactants and the products. For reaction 2, the energy difference between the reactants and the products is right here. They have the same change in enthalpy because the energy difference between the reactants and the products is the same. Check out this thermite reaction movie, then we'll answer some questions. Would you classify this movie as an endothermic or an exothermic reaction?
Aluminum metal is a very strong reducing agent. The flower pot contains thermite, a mixture of finely ground aluminum metal and iron 3 oxide, plus a starter mixture containing magnesium metal. The reaction is initiated by igniting the magnesium metal ribbon. Some of the molten iron has flowed out through the bottom of the flower pot into the bucket of sand.
That was definitely an exothermic reaction. So that means the products must be at a lower energy than the reactants. And that's what this plot is saying. The products are at a lower energy than the reactants. So on this plot, see if you can sketch in the energy of activation and the enthalpy for that reaction, and see if your answers agree with mine. The energy of activation is always the energy that the reactants must overcome. So if I start at the reactants, the energy they must overcome is EA. Enthalpy of a reaction is the energy difference between reactants and products. So we'll just see where the products are in this energy, and sketch an arrow between their two different levels, and that would be the enthalpy of a reaction. Is this reaction endothermic or exothermic, and why? Well, it's definitely exothermic because my enthalpy is less than 0. It's negative. For the thermochemical equation above are reactants or products at lower energy. It's exothermic, so it gave off a lot of energy in going to products, so products are definitely at a lower energy. If 2 moles of aluminum react, what is the change in enthalpy? A strange way of asking a question, but we just need to get used to it. All they're asking for is heat. They want us to convert 2 moles of aluminum to heat. And remember, heat has units of joules, but also kilojoules. So all we're going to do is start with the measurement, 2 moles of aluminum. We need a conversion factor of moles of aluminum to kilojoules. And it's right here, using your mole bridge. 4 moles of aluminum for negative 300 kilojoules. 4 moles of aluminum, negative 300 kilojoules. So I get about a negative 150 kilojoules. So when 2 moles of aluminum react, about 150 kilojoules of heat is given off. If 1 mole of aluminum oxide is produced, what's the change in enthalpy? So I have 1 mole aluminum oxide. So I need a mole bridge between moles of aluminum oxide and heat. Now I have 2 moles for every negative 300. So again, I get a negative 150 kilojoules. If 1 mole of oxygen reacts, how much heat is released or absorbed? So remember, heat has units of kilojoules. So all we're going to do is convert 1 mole of oxygen into kilojoules. So heat is just another word for enthalpy. It's the same type of problem, just different wording. So 1 mole of oxygen, we need to convert moles of oxygen to kilojoules. And my ratio is 3 to negative 300. I get negative 100 kilojoules. If 3 grams of aluminum react, what is Q? So again, another way of asking the same question, all we're doing is converting 3 grams of aluminum into kilojoules. So we start with the 3 grams of aluminum. I know I'm going to need to use a mole bridge, so let's get it into moles of aluminum first. And then my mole bridge in getting moles of aluminum to kilojoules. The molar mass of aluminum is 26.6. And I know that I have 4 moles of aluminum for every negative 300 kilojoules. 4 moles of aluminum for every negative 300 kilojoules. So 3 divided by 26.6 times 300 negative divided by 4, about 8.46. That's negative kilojoules. So if 3 grams of aluminum react, about 8.46 kilojoules of heat is given off. Given the below thermochemical equation, what is the change in enthalpy for each reaction? So here's our thermochemical equation. And all we're going to do is mess with the reaction and see what the effect is on delta H for that reaction. So the first one, A, what do we do to the reaction? We flipped it. Right? We flipped it. So the reactants became products, the products became reactants. All we do is change the sign on delta H to get the right answer. So all we did is flip the reaction, just change the sign on delta H. What was done to get B? They multiplied through by 2, right? So all we do is multiply delta H by 2, negative 600 kilojoules. How about C? What was done? They multiplied through by 1/2. So multiply delta H by 1/2, and negative 150. How about this last one? They multiplied through by 4. 4, and they flipped it. So all we do is multiply our delta H by 4 and flip the sign. Positive 1200 kilojoules. When 1 mole of iron metal reacts with hydrochloric acid at constant temperature and pressure to produce hydrogen gas and aqueous iron 2 chloride, 87.9 kilojoules of heat evolves. Write a thermochemical equation for this reaction. So remember, thermochemical equation just means we have a reaction with an enthalpy. Now we know the enthalpy is going to be 87.9 kilojoules. Is it positive or negative? The answer is it evolves. It's given off. Okay? Now identify the reactants. Iron metal react with hydrochloric acid to produce hydrogen gas and aqueous iron 2 chloride. So we should have an aqueous here too then. Is it balanced? Just put a 2 in front of there. So here's our thermochemical equation. 1 mole of iron reacts with 2 moles of hydrochloric acid to produce a mole of hydrogen gas and a mole of iron 2 chloride, giving off 87.9 kilojoules of heat. Given the below thermochemical equation, what is the change in enthalpy for the reaction involving only 1 mole of tetraphosphorus dicoxide? Write the thermochemical equation. Well, if we want this to be a 1, pretty much just multiply everything through by 4, right? And we'll have it. So we'd have tetraphosphorus dicoxide plus 12 halves, which is 6 moles of water, plus 4 moles of phosphoric acid, and multiply negative 113 times 4, get about 452. The average speed of a chlorine dioxide molecule at 25 degrees Celsius is 360 meters per second. What is the kinetic energy in joules of a chlorine dioxide molecule moving at this speed? Okay. Remember what I said earlier. The kinetic energy, that'll be in joules. The mass of the molecule had to be in kilograms, and the speed in the meters per second. So we've got the speed. So my kinetic energy is going to be 1/2 the mass of that molecule in kilograms times the speed squared, 360. We just need to find the mass of one molecule. Do you remember my suggestion? The mass of that one molecule is just the molar mass of chlorine dioxide, all over Avogadro's number. So the molar mass of chlorine dioxide, 35.45 plus 32, about 67.45 grams per mole. Divide that by Avogadro, 6.022 times 10 to the 23rd per mole. So my per moles will cancel. I'll just get grams. 67.45 divided by 6.022 times 10 to the 23rd, 1.12 times 10 to the negative 22 grams. But I need my mass in kilograms, so 1.12 times 10 to the negative 22 grams. I got 1,000 grams a kilogram. So move decimal place over 3 more places. I'll get 1.12 times 10 to the negative 25 kilograms. And that number goes up here. So after I plug everything in, I got my kinetic energy to be 7.0 3 times 10 to the negative 21 joules. A very small energy, but it's a very small molecule, even though it's moving pretty fast. The process of dissolving ammonium nitrate in water is an endothermic process. What is the sign of Q? Well, it has to be positive, because it's endothermic. If you were to add ammonium nitrate to water in a flask, would you expect the flask to feel warm or cool? Well, if it's endothermic, you need to get cool because heat's getting absorbed in order for the reaction to progress. A bullet has a mass of 245 grains and is moving at 2.52 times 10 to the third feet per second. Calculate the kinetic energy of the bullet in joules. So it seems straightforward, it's just that all the units are messed up, right? So I need to know my mass in kilograms. I need to know my speed in meters per second and then square it. So let's see if we can do those conversions. M has to be 245 grains. And I know in 1 grain, I have 0.0648 grams. And I need to go to kilograms, so I might as well go there. 1,000 grams in a kilogram. About 0.0159 kilograms. There's my mass. Now my speed, 2.52 times 10 to the third feet per second. The seconds are fine. It's the feet I got to get to meters. So in a foot, I have 12 inches. And then in an inch, I have 2.54 centimeters. 1 inch, 2.54 centimeters. And I know there's 100 centimeters in a meter. About 768 meters per second. So as a final answer, square the 768 times 0.0159 times a half, 4.7 times 10 to the third joules. Okay, so there's a range of different types of problems here. One is this kinetic energy type of problem. And remember, to get the mass of a molecule, just divide the molar mass by Avogadro's number. We've seen that we can manipulate these thermochemical equations. We can flip them, multiply them through by 2 or 3, and just know what the effect is on the enthalpy of the reaction when you do that. Have a feeling for these energy plots. Be able to recognize the energy of activation or sketch in the enthalpy of the reaction. And know whether a reaction is endothermic or exothermic when given these plots. So good luck.